so then we now go to the third presentation in this session, which is a short tool presentation. So the speaker is Oyendrila Dobe, and I'm really sorry if I pronounced it wrong. So you're supposed to have about so 10 minutes in total, so like 7 minutes for your presentation, yes. And then a few minutes for questions. Okay,
absolutely.
And she will talk about HyperProb.
Yes. Can you see my screen? Okay, and can you hear me? Okay.
Yes, everything fine. Go ahead.
Great. Thank you so much. So I'm going to present our prototypical tool paper. This is joint work with Erika, Ezio, and my advisor, Borzu. Okay, so essentially most of the works that I've seen here in FM deals with trace properties. So most of you know what's a trace property. But the problem with trace property is it cannot express relationships between traces. Hence, we need the concept of hyperproperties, which has been going on since, as cited in previous work. It essentially gives you a set of sets of traces, and it's a system property. So for example, in a linear logic, if you want to express that I drink coffee every day at the same time, you want to say that for all state combinations that you have globally, coffee should appear at the same time. So if your system can produce this kind of a trace set, you can see that if you pairwise compare each of the traces, not all of them agree on when you drink coffee. Hence, clearly, this system does not satisfy this property. So moving on to specific probabilistic systems that I work on, HyperPCTL is used to express probabilistic relationships between traces. In terms of our grammar, we quantify, since we allow non-deterministic systems of MDPs, which Pranay just defined. MDPs, we initially allow scheduler quantification of for all or exists, followed by state quantifications, followed by a non-quantified part of HyperPCTL. So for an example, if this is an MDP and you have alpha and beta at the initial states, and you have different probabilistic distribution following the non-deterministic action, if I'm looking for a property, say for all schedulers and for all state combinations, starting from initial states, if my value of H is different, I still should be able to reach a state with labeled as L equals to 1 with equal probability. If you look at B, this happens, but however, if you're choosing the scheduler A alpha, it does not happen. Hence, this MDP does not satisfy the given property. So in terms of our approach, general model checking of HyperPCTL in MDPs is undecidable due to the extra expressivity that HyperPCTL provides. Hence, we have restricted the type of schedulers that we allow to non-probabilistic memoryless schedulers. In HyperProb, the approach is that given your MDP and given your HyperPCTL formula, we convert it into an SMT encoding, and we can say that the MDP satisfies the given formula if and only if the SMT encoding that we generated is satisfied. Currently, in our prototypical implementation, HyperProb allows just one scheduler quantifier, either one for all or exists, and as many as state quantifiers as you want. So an overview of what goes on inside the tool, you given an MDP model and you given a hyperproperty in HyperPCTL. The model we parse using StormPy, and hyperproperty is parsed into an abstract syntax tree using the Lark library in Python. Using the parsed model and property, we first encode the scheduler choices that are available at each state. Further, we encode the state quantifier combinations that are allowed in your property in relation with the data provided by the model. And we encode the non-quantified part of temporal logics and state and path formulas in your property. All of these encodings essentially generate Z3 constraints, which when fed to Z3 gives us a solution, a Boolean result first saying whether the property is satisfied or dissatisfied. And in specific cases, you can get a counterexample or a witness. So essentially the input that we give, we currently support our only Prism models that StormPy parses for us, and HyperPCTL formula that we insert as strings. The output gives you a Boolean result and counterexample or a witness in specific cases. The main idea is if you have a exists scheduler formula, we directly encode the property that is given. However, if you have a for all formula, we negate the rest of the property and try to find out if the property is not satisfied. So if the negation is not satisfied, we can say that for all, we could not find a counterexample, hence the property is satisfied in that case. So since due to the lack of time, I want to show just a sample of how we run the code. If you're calling the source file, you initially have to give the address of the model file that you have as a string. You have to give the property using our grammar. On running, initially after parsing the model, it gives you details on the states, transitions, and actions available in the model, and it tells you what steps it is going through. And finally, after checking or getting a result from the Z3 solver, it tells you whether the property holds. And if it doesn't hold or hold, depending on counterexample or a witness, you essentially get a sequence of actions that you should be choosing at every step of the MDP to get a DTMC, which in this case will give you the counterexample for your property on the model. And finally, we give some statistics based on what the time is and how many variables or formulas we have been checking. So moving to the evaluation, since we do not have as such any existing approach that solves the problem in our way, we are just comparing it with the data that we have from our theory paper back in ATVA. So the idea, since we included a lot of optimizations when building this tool currently. So as you can see, one of the main things that I want you to notice is this is the encoding time. N represents our previous normal approach and O represents the optimized approach that we have now. So in that case, because of optimizations where we do not encode all state combinations, we encode only the necessary state combinations depending on the relevant quantifier in the formula. The number of encoding that we have to do essentially decreased by a huge factor, which, since we do not have as much control over Z3's solving, on optimizing this, we could reduce our total running time by a huge factor. And for most cases of timeouts, here we were able to scale the models and solve it. And also the number of variables that we finally generate, which essentially leads to the reduction of the running time, is almost by a factor of 1/3. So, and due to lack of time, if you want to know the details of case studies that we have, I'd like you to refer to our paper. And so to conclude it, we have presented a SMT-based model checking algorithm, which is NP-complete if you have an existential scheduler quantifier and co-MP-complete if you have a scheduler universal quantifier. And we have provided a Docker in our link for the tool, which is open source, and it comes with all the pre-installed dependencies that we have, like Lark or StormPy and its existing dependencies, which makes it easier to directly run the tool. And thank you for listening.
Oh, thank you for your nice presentation. It's not easy in such a short time. You did it very well. So let me see. Is there no question in the chat? No one raised his hand, apparently. I think all the presentations in the sessions are so clear that no one has any questions. Or maybe it has to do with the fact that we are on Friday now. Anyway, so you only managed. So if I understood well, you did not you were not able to compare to any other tool because you're the only ones doing this, but you presented it, you compared it with the theoretical results from an earlier paper. Was that the comparison?
Yes. So this was the result from our theory paper where it was not the implementation was not quite optimized as we have it right now. So
it was hence like
we had to include a lot of optimization. Yes. Okay. Exactly. Yes.
Okay. Good. Yeah, that's a nice improvement then.
Yes.
Okay. Yeah, so I have no further questions, and in the interest of time, I think it's good if we move on. So thanks a lot for this nice presentation.
Thank you.
And